Hello friends, so today we are going to solve question from modern physics, and these questions are from the year 2022. So total 10 questions we are going to solve, and all these 10 questions are from the mains. And for the year 2022, this is part 2. In the part 1 we solved around 31 questions, and those questions were also from the mains. And we are left with advanced question from 2022. So we'll try to cover that in the next part. Okay. So the first question, it states that in a reactor, 2 kg of 92U235 fuel is used up in 30 days. The energy released per fission is 200 mega electron volt. Given that Avogadro number N is 6.023 into 10 to the power 26 per kilo mole, and 1 electron volt is 1.6 into 10 to the power minus 90 joule. The power output of the reactor is close to. So in this case, we have to find out basically what will be the power output. And for that, first of all, we are going to find out the total energy released. From there, we can easily calculate our power output. And so let's find out, because we are given that there is a 2 kg of uranium and it is having whose mass is 235. Okay, so we start from there only. We can say molar mass of U35 molar mass of U35 235 is our 235 kg per kilomole. So the number of kg that is given to us is our 2 kg. So we are going to find out number of moles in 2 kg. Okay, so we can say, or because the Avogadro number is mentioned in our kilomole, therefore we are going to find out number of kilomole in 2 kg. Number of kilomole in 2 kg. Let us suppose that is given as small n, and the small n will be equal to 2 divided by 235, and this will be approximately equal to 0.00851. From here we can easily find out the number of atoms in this 2 kg. Okay, because Avogadro number is given to us, therefore we can say that number of atoms will be equal to, we have small n multiplied by capital N. Small n is our 0.00851. Capital N is given to us as 6.023 into 10 to the power 26. And so we get number of atoms. Let us write it as capital N, and atoms will be equal to 5.12 into 10 to the power 24. Now we are given that energy per fission is 200 mega electron volt. Okay. So we are given that energy per fission is our 200 mega electron volt. So we can write this as a 200 10⁶ electron volt. Now we convert this into joules. So therefore we can write energy from the fission will be equal to 200 10⁶ multiplied by 1.6 into 10⁻⁻19, and this will be coming as 3.2 into 10⁻⁻11 joules. Now we can find out the total energy released. We can say our total energy released, let us call this as E total, that will be equal to number of atoms multiplied by energy per fission. So from here we get our ET, total energy is equal to number of atoms is 5.12 into 10⁻24 multiplied by per fission is our 3.2 into 10⁻⁻11. So this energy per fission, total energy released will be coming as 1.6 into 10⁻14 joules. Now we can easily find out our power because we know the time. Therefore we can say power is equal to total energy upon time. Total energy is our 1.6 into 10⁻14, and time is given us as 30 days. So we can say 30 multiplied by 24 multiplied by this 3600. So this will be entirely in seconds. So this will be approximately equal to 6.32 multiplied by 10⁻7 watts, or in terms of megawatt we can write this will be our 63.3 megawatt, or approximately we can say option number 3 is correct. You can just approximate it as a 60 megawatt. So option 3 is correct. 3 is correct. Next question. It states that in a radioactive material, fraction of active material remaining after time t is 9/16. The fraction that was remaining after t by 2 is. So this is directly based on our you can say radioactive decay law. So we can say radioactive decay law, and it says that after time t, let us suppose the amount that is left is n of t, which will be equal to the initial amount and e⁻⁻λt. So we are interested only in the fractional part, so we can just convert this into fraction. So we can write our remaining amount, original amount, is equal to e⁻⁻λt, and after time t it is given as 9/16. Okay, so we can write that after time t, this fraction, that is nt upon N0 is said to be 9 upon 16. And from here we can say that e raised to power minus lambda t will be equal to 9 upon 16. And in the second case, we have to find out the fraction that was remaining after time t by 2. Okay. Therefore, we can write that fraction remaining after time t by 2. So in place of t, we can easily write now as t by 2. So this comes as n t by 2. Initial concentration will be over N0 is equal to e raised to power minus lambda t by 2. Now on the right side, we can just manipulate it, and this can be written as our e raised to power minus lambda t and whole raised to power 1 by 2. And this value we already know. This value is our 9 upon 16, and this comes as 1 by 2, which is basically square root. This will be coming as 3 by 4. So option number 1 is correct. One is correct. Next question. It states that the radius of radius r of a nucleus of mass number A can be estimated by the formula r is equal to 1.3 into 10 to the power minus 15 a raised to power cubic root. It follows that the mass density of the nucleus is of the order of. So from the radius, we are basically going to find out what will be the order of the density. Okay. So first of all, we are going to find out the volume. So volume, if we represent it as V, will be equal to our 4 by 3 pi r cube, where r is the radius which is given to us. So we substitute it, we get our volume V is equal to 4 by 3 pi, and we get this as 1 by 3 into 10 to the power minus 15, and this is our whole cube, and this comes as a raised to power 1 by 3, and this also is a whole cube. Here 1 by 3, this 3 goes away. And so at least from here, everything will be constant. We can say that our volume is proportional to our A, where A is our, we can say, mass number. And from the mass number, we can also find out our nuclear mass. So we can say that our nuclear mass is equal to A multiplied by MP, okay, where this is our mass of a proton or neutron, okay, and that is approximately your 1.67 into 10 to the power minus 27. So we can write this as A multiplied by 1.67 into 10 to the power minus 27 kg. Now we can just find out our density, because we know mass and we know our volume. So we can say that our density is equal to, let us call this as capital M. Capital M oblique volume, which comes as our A into 1.67 into 10 to the power minus 27, and denominator comes as 4 by 3 and we have 1.3 into 10 to the power minus 15 whole cube multiplied by A. And here this A and A cancels out, so our density, that is our rho, will be approximately equal to 1.82 into 10 to the power 17 kg per meter cube, or order we can say 10 to the power 17. Therefore option number 3 is correct. Option 3 is correct. Next question. It states that, we already did this. Next question. Find the binding energy per nucleon for 120 to 50 SN. Mass of proton is given, mass of neutron, and mass of nucleus of SN is also given. Okay. So we are given, you can say this is our SN, and we have this as 120 and 50. So from here we can say our Z will be equal to 50, N will be equal to 70, and our A will be equal to 120. And we have to find out the binding energy. So for that we are going to use our mass defect. Okay. And first of all, let us find out with respect to the nucleon masses. So we can say that our nucleon mass will be equal to Z multiplied by mass of proton plus N multiplied by mass of our neutron. Okay. So we simply substitute the values. Z is our 50, mass of proton is given as 1.00783, plus N is our 70, mass of neutron is our 1.00867. And this comes as our 120.9984 AMU. Now we can use our mass defect. So we can say mass defect, that is our delta of M, is our, this is 190, so this comes as 120.9984 minus 119.9021. Okay. And this delta M will be equal to 1.096201. Therefore binding energy will be mass defect multiplied by 931, total binding energy. So we can say that total binding energy will be equal to delta M multiplied by 931, which gives us 1.096201 multiplied by 931. And we are supposed to do it for our per nucleon. Okay, so from here we can write that our binding energy per nucleon will be equal to total binding energy, that is 0.096201 201 multiplied by 931 and divided by A, and A is our 120. So this comes as approximately equal to 8.5 mega electron volt. So option number 2 is correct. Two is correct. Next question. It states that the activities of three radioactive substances A, B and C are represented by the curves A, B and C in the figure. Then their half-lives ratio of A, B and C are in the ratio. Okay, a basic curve is given to us. We have A, B and C, and on the x-axis we have years, on the y-axis we have natural log of R. So in this case we are going to use our basic formula, and that is with respect to our activity. So we can say activity at a time t will be equal to over A0 e raised to power minus lambda t, and because we have to represent it in the formation of something like a line, so let us take, we can write this will be equal to over lambda t will be equal to natural log of A0 upon A, and we can further simplify it. We can write lambda t is equal to natural log of A0 minus natural log of A. Okay. And let us rearrange the equation, and that rearrangement is going to give us, one second, I missed something. Yes, so this is time t. Therefore I can write it as natural log of AT will be equal to minus lambda t plus natural log of A0. Now we can just compare it by our standard equation, that is y is equal to mx plus c. So by comparison we can say that y is equal to, one second, I think I missed something. It looks good. We are mainly interested here in slope, so let us directly put our slope, which is our m, which is equal to our minus of lambda, and slope is also represented as our tangent of theta. Okay. So we have three graphs A, B and C. So let us find out what will be their respective slopes. So we can say for A, let us call this as MA, which will be equal to this tangent of theta A, giving us, this is our 6 upon 10. So this will be coming as 6 upon 10, which can be written as 3 upon 5. And for B, we can write this as our MB is equal to tangent of theta B, and B is our, it is also upon 6 upon 5. And finally we are having a C, which is of M of C is equal to tangent of theta C, and C will be equal to 2 upon 5. Therefore this will be our lambda A, this will be our lambda B, and this will be our lambda C. and standard formula for half-life we already know. So we can say our T half is equal to natural log of 2 divided by lambda. And we can divide this into our three parts, and that is our T half of A ratio T half of B ratio T half of C. And from here we can write this as our T half of A is our 5/3 because lambda is in the denominator, so this will be coming as 5/3. B is our 5/6 and our C is our 5/2. And from here we can just conclude, or we can write the answer that this 5 goes away if you multiply thoroughly by 6, so this will be left as 2, this will be left as 1 multiplying by 6, and this will be left as 3. So this will be 2:1:3. So option number 1 is correct. One is correct. Next question. It states that a radioactive nucleus decays by two different processes. The half-life of first process is 10 seconds and that of second is 100 seconds. The effective half-life of the nucleus is close to. So this is quite straightforward based on our two processes. First process, let us suppose we have lambda 1, and for the second we have our lambda 2. So the effective will be lambda 1 plus lambda 2. Okay, we have to keep in mind that the processes should be two different processes or independent processes. So we start with our decay law. And this decay law states that our lambda is equal to natural log of 2 divided by T half. So we are having two decays. So let us say that for lambda 1 we get this as our natural log of 2, and this is T half for first, then we have second lambda 2 natural log of 2, and this is our half-life for second. And these are two independent processes, so we can say effective is equal to lambda 1 plus lambda 2, and our effective can be written as natural log of 2, and let us call this as our T half effective. And we are supposed to find out effective half-life. Okay, so let us first of all find out lambda effective, and so we substitute the value of our for the first and as second. So we get a lambda 1 will be equal to, this will be 0.693 divided by 10. Lambda 2 will be equal to, this is 2, 0.693, for the second is our 100. So we get that our lambda 1 will be equal to 0.0693, and we have lambda 2 will be equal to 0.0693. Therefore our lambda effective will be equal to 0.0693 plus this is our 0.00693, and this will be coming as equal to 0.07623 per second. So we can use now this formula, and let me rewrite in the formation of our T half effective. So we get T half effective will be equal to natural log of 2 divided by lambda effective. This comes as 0.693. Lambda effective is 0.07623. So this will be coming as 9.1 seconds. So we have this as option 2 is correct. Option 2 is correct. Next question. It states that you are given the mass of lithium as 7.0160, mass of helium and mass of hydrogen. When 20 grams of lithium is converted into helium by proton capture, the energy liberated is. Okay, so in this case, we have to find out the energy liberated, and for that, we have to find out, or basically, we are going to use mass defect, and from there we can easily find out the energy. Okay, and okay, so we are given that lithium is converted into our helium with the proton capture. Okay, so we can write the reaction approximately. We can say our lithium is capturing a proton. This is giving us a helium. Therefore, we can find out our initial mass, and so initial mass let us call this as Mi will be equal to, for lithium, that is 7.0160, and for proton we are also given as, that is basically a hydrogen, 1.0079. So we get this as our initial mass will be equal to 8.0239, and from here we get our final mass. So we can say our final mass, let us call this as MF, will be equal to, and this is our helium, which comes as 2 times 4.026. So we get our final mass will be equal to 8.0052. Now we can find out mass defect per reaction. Mass defect per reaction, that is our delta M will be equal to, our final is this comes as 8.0239 minus 8.0052, which gives us that our delta M is equal to 0.0182, and from here, because this is mass defect per reaction, so from here we can find out energy per reaction. per reaction, and let us call this as a E, and then this E will be equal to our delta M multiplied by 931, which comes as 0.0182 multiplied by 931, and this will be coming as 17.4097 mega electron volt. Now this energy we are going to convert into joules. So we can say that energy E will be equal to 17.4097 multiplied by 10 raised to the power 6 and multiplied by 1.6 into 10 to the power minus 19, and this now is in joules. So we get this energy will be equal to 2.78 into 10 to the power minus 12 joules. Now we come to the question, and it states that there is a 20 gram of this lithium. Okay, so we can say that our number of lithium atoms in 20 grams. Number of lithium atoms in 20 gram, and for that we are going to use our molar mass, and we are going to find out moles. For that we are going to use molar mass. So let me write that our moles is our given mass, that is our 20, and molar mass is our 7.0160. So number of moles will be coming as 2.85 moles. Now we can find out that number of atoms, or basically number of reactions. So we can say number of reactions will be equal to moles multiplied by the Avogadro's number, that is 6.022 into 10 to the power 23, and this comes approximately equal to as 1.71 into 10 to the power 24. Now we can find out the total energy, because number of reactions we know and energy per reaction is also known to us. Therefore we can say that total energy will be equal to our, let us call this as ET, is number of reaction, that is 1.71 into 10 to the power 24, and per reaction is our 2.78 into 10 to the power minus 12. So this gives us that our total energy will be equal to 4.78 into 10 to the power 12 joules, and we are supposed to do it in kilowatt hour, so that is quite simple now. So we can say our total energy in kilowatt hour will be equal to 4.78 into 10 to the power 12 divided by 3.6 into 10 to the power 6, and this is approximately 1.3 into 10 to the power 6 kilowatt hour. So this is 1.33. Option 1 is correct. One is correct. Next question. It states that given the mass of various atomic particles, proton, neutron, electron, where P is a proton and a neutron, E is electron, and this is our anti-neutrino, and D is our deuterino. Which of the following processes is allowed by momentum and energy conservation? So this question is directly, and the hint is itself given. We have to check with respect to momentum and energy conservation. Okay, more or less we can just make a approximate guess based on our energy conservation. Okay, and first is our n plus n is going to give us a deuterium atom. Okay, and in this case it means this one neutron and okay, yes. So if we try to find out, let us take this as option number 1. The exact reaction that should be is in this case one of the, in option number 1, one key element to balance according to the conservation of energy or momentum is our, okay, let me write it first of all. So we can say that to convert one neutron to a proton, we need beta decay. So in terms of reaction, we can write that the neutron will be converted to our proton, this will be electron, and we are going to have our anti-neutrino. Okay, so the reaction that is given to us is basically does not satisfy our energy conservation. Okay, so therefore this option 1 is incorrect. Now we come to the option 2. Option 2 states that our N plus P is going to have D plus gamma, and let us check it with respect to the masses. So we get our mass of N plus mass of P, this will be equal to 1.0087 plus 1.0072, and this gives us 2.0159, and our MD, mass of our product side, that our MD is, it is given to us as ME. I think I didn't, there is some, okay, anyways we know the MD, and this MD is our 2.0141. So if you compare the mass, we can say that our MD is, mass of MD is less than our MN plus MP. Okay, and therefore from here we can say that energy will be released. Energy will be released, and it satisfies our conservation and momentum. Satisfied energy conservation, or we can also say the momentum. Therefore, option 2 is correct. And we come to the part 3, and part 3 gives us proton gives us neutron plus. Okay, proton gives us neutron plus, and this is E positive. Okay. And in this case, our MP is our 1.0072, and our Mn plus Me positive will be equal to 1.0087 plus 0.005482, and this will be equal to 1.0092. So from here we can say that our product mass, that is Mn plus Me positive, is greater than our reactant mass, which is energetically not possible. So we can say conservation of energy fails. Or let me write it directly, that energetically forbidden. Forbidden. So therefore option number 3 is incorrect. And we come to the final option, that is option number 4. This gives us that our plus E negative is going to give us a gamma. Okay. So this also energetically will be forbidden. Okay, so option number 4 is also incorrect. So option 2 is the correct option answer. Option 2 is correct. Next question. It states that the activity of substance changes from 700 per second to 500 per second in 30 minutes. Find its half-life in minutes. So here we can use decay law in terms of the activity. So we can say our decay law, we state that the activity at a time t will be equal to initial activity A0 e raised to the power minus lambda t, and we can find out their ratio. So we can say our A of t upon A0 will be equal to e raised to the power minus lambda t, and it states that activity changes from 700 to 500. So which basically means that our initial activity, that is our A0, is our 700, and final activity after time t, which in this case is 30, is our 500, and time is our 30 minutes. So we have to find out the half-life. So we can write this as our 700 upon 500 is equal to e raised to the power minus lambda, and this is multiplied by 30, and we can say e raised to the power minus lambda 30 will be equal to, this is our 0.7143, and we can easily calculate our lambda from here. We get this as our minus 30 lambda is equal to natural log of 0.7143, which will equal to minus 0.3365. Therefore, our lambda is equal to 0.3365 divided by 30, and this comes as 0.01122 per minute. From here, now we can easily calculate our half-life. So we can say our T half will be equal to natural log of 2 divided by lambda. This is our 0.693 and 0.01122. Approximately will be equal to 61.8 minutes. So option number 2 is correct. Next question. It states that two gases, argon atomic radius 0.07 nanometer, atomic weight 40, and xenon atomic radius 0.1 nanometer and atomic weight 140 have the same number density and are at same temperature. The ratio of their respective mean free time is closer to. So here we are supposed to find out the mean free time, and the mean free time is represented as tau. So we can say that mean free time, which is our tau, will be equal to lambda upon and this can be written in terms of proportionality, 1 upon n times sigma and multiply by square root of m. Because, okay, so let me write it separately also, because we know that our mean velocity is proportional to square root of mass and our lambda is proportional to our n multiplied by sigma. So we are given that we have same number density, that is value of n is same. Okay, so here we are given that same number density, so it means n will be same, and also we are given that our temperature is also same. So we can write that our tau for ratio, we can write it as tau for argon divided by tau for our xenon will be equal to, this can be written as our mass of argon, mass of xenon multiplied by rho for our sigma for xenon and sigma for our argon. And we know that for our solid mass or hard spheres, the sigma is directly proportional to our radius square or diameter square. So we can say that for hard spheres, which is something like a nucleus, we can write that it is proportional to our d square and proportional to our radius square. And 1 second. Okay, so therefore we can write that xenon for argon will be equal to our radius for xenon, radius for argon, and its whole square, and these values are given to us. So this comes as 0.10, 0.07 whole square. So this comes as approximately equal to 2.0408. Now we can just find out there, because their atomic weight scale is also given to us. So let me calculate that also. So we can say square root of mass of argon divided by mass of xenon is equal to square root, this comes as our 40 upon 140, approximately equal to 0.5345. So we got both the values. Now we can just simply multiply them. Therefore we can say that mean free time for our argon and our xenon will be equal to 0.5345 multiplied by 2.0408, approximately equal to 1.09. And this is actually very far from the answer. Okay, I forgot to put the options. So the actual value is 1.09, but the option that is given, anyways, it doesn't matter. Okay, so I think I forgot to put the option. So this comes as 1.09. Okay, or if required, this can be approximately equal to as 1. I'm not sure what will be the option, but the process will be, or the calculation will be the same. So this completes the 10 questions for the year 2020 part 2nd. In the next part, we are going to solve for the advanced versions. So this completes the part 2nd for the year 2020. Thank you.